This conference will now be recorded.
Okay, so hello and welcome to this webinar. My name is Jonas and I am an FE at Know-How. And in this webinar, I will show you how to debug and trace a target with multiple cores in Trace32. And if you have any questions, just type them in the chat window and I'll answer them in the end. So a little bit about Know-How. We have been around since the 80s. We have offices in Sweden, Denmark, and Finland. And on the upper right picture, you can see the areas that we are mainly operating in. So we are distributors for embedded systems tools. And some of our products includes compilers, debuggers, and code testing. So that can be unit testing or static code analysis and so on. And we also have tools for CAN, Bluetooth, and USB. And for those of you who are interested, you can just enter our website, knowhow.sc. So in order to debug a target in Trace32, you need the debugger unit. So the one that you can see in the picture, this is an universal debugger unit. So it works for all architectures. And then you will also need a specific debug cable for your architecture. So today we are using an ARM architecture. And with this setup, you can do basic debugging like looking at and changing contents in memory, registers and stack, etc. And you can also step or break or control the runtime execution. And if there is an on-chip trace on the target, then you can also use trace features if you have a license for it. But you should keep in mind that the on-chip trace buffer is usually pretty small compared to an off-chip trace. So it's more limited in what you can do. And if you want to use the off-chip trace, then you can add a trace module. You can see one in the picture. So this is also a universal hardware, so it works for all architectures. And you will also need a architecture-specific preprocessor. And you would simply plug in the power trace unit into the power debug unit. The debugger unit. And these off-chip trace usually have a couple of gigabytes of trace memory. So a short explanation of trace for those of you that don't know. Trace is like a recording of the system when it is running. So with trace, you can record system information in a non-intrusive way. And you can also see detailed information about the executed instructions. And you can also see memory reads and memory writes and so on. And there are, of course, different features in trace. And this depends on what is actually implemented and supported by the chip. So this is the setup that I'm using today. We have a debug unit and a trace unit and preprocessor and a debug cable. And our target is a Ultra 96 with 4 A53 cores and 2 R5 cores. And actually I'm connected via Ethernet today, not an USB. But that's just a minor detail and it doesn't change the way that Trace32 works. So SMP stands for symmetric multiprocessing. And this is what you would use when you debug a system with multiple identical cores. And all of the cores share the same OS. And in this case, we will only have one Trace32 instance. So now I'm going to switch to Trace32 and show you a little bit about SMP debugging. So we will debug with 4 A53 4 A53 cores. So now I'll run a script that we have prepared. And this script just set up configurations for the target. So usually they are provided by Lauterbach, so you don't need to write them from scratch. You just need to edit them a little bit. I just want to check that I loaded the right file. Okay. So one important command you need to know is the command to assign which cores that you want to debug. And it is called core.assign. And after you type space, then it gives you all the available cores. So let's say we just want to debug 2 cores. Then we would simply assign core 1 and 2. And down here, you can right click, and here you will see the available cores. So let's go back and assign all of the 4 cores. Okay, so in the list window, then you will see which core is currently selected. So you would simply switch between the different cores down here to see where the different cores are standing at. And if you want the list window to show a specific core, then you would simply add this option, core 1, for example. And now this window will always show core 1. And the same thing works for the register window and the stack window. So if you add the option, then it will show only the core that you have selected. And if you don't have the option, then you simply switch to the bottom right. And I also want to show you this command called target system.state. And in this window, you can see the status of all the cores. Oh, and now I want to show you what happens when you are stepping in the list window. So when you're stepping in the list window in mixed mode that we are currently using right now, then we will only step the selected core. But if we switch to high level mode and we step, then you will see the core is getting stepped in this window too. So we're stepping all cores. So this is something to keep in mind. And now let's say we want to put a breakpoint at a specific function. Let's say sieve, I want to put just somewhere. When we run and hit this breakpoint, you will see that we are stopping regardless of which core is actually hitting this instruction. And if you want to only break when a specific core is hitting this breakpoint, then you should change breakpoint here and use this advanced field. And the command for that is core equals and the number that you want. So let's say 3. And now it will only break when it is core 3. And if you look down here to the bottom right, you will see that there is a S that is blinking. And if you look closely, you also see that there are like yellow stripes on the breakpoints. I'll run it a little bit so you can try to see. There's a blinking S down here. It means that the breakpoint is intrusive. So every time we hit this line, the debugger is pausing the CPU, and I think it takes a couple of milliseconds to check which core it is that is actually executing this instruction. So that's just something to keep in mind. You don't want to use intrusive breakpoints if you can help it. But in this case, you would have to. So let's remove this breakpoint. And let's empty the trace buffer and just start a new recording. So all of the cores are traced now in the trace buffer. And we use trace.list to show the data in the trace buffer. So the trace packets are shown in a chronological order. So the latest trace data are shown at the bottom. The further up we go, the more the data in the past are shown. And you can see in this line here which core this trace packet belongs to. So we have trace packets for all of the cores. And let's say we want to find all of the entries to the sieve function, then you should use this find button. And here you can type sieve, or you can use this drop-down menu. And if we press find all, then we will find all the entries into the sieve function. And in this line here, you can see which core number it is. So let's say we want to find all the entries that core number 3, we only want to find the entries that core number 3 did. Then we should use this option, core 3. So now we only have information from core number 3. And again, we would press find and type sieve and press find all. And now we will only get the information from core 3. And now I want to show you another window. It is called trace.chart.symbol. And in this window, you can also see for all of the 4 cores. You can see it's a 0 here. If you go down, you'll see core 1, core 2, and core 3. And they also have different background colors. And in this window, you can see the program flow if you scroll in. So for example, you want to know how much time it took from here to here. you would simply highlight it and drag it, left click, drag it with your mouse. And down here to the left, you can see how much time it took. And let me bring up the trace.list window again. I want to show you this option that is called track. So when I right click this window, we'll get the command to bring it up. And when I type track here, then we'll simply edit the window. If you don't right click here and you just type t.l, then it will open up a new window. So that's just two different ways of doing the same thing. But now that we have the track option, and let's say we are looking at somewhere that we think is interesting, and when we left click, when you have the track option, it will, all of the windows that have the track options will jump to the corresponding spot. So in this case, we're clicking somewhere at course 0, and we can zoom in and see what happens. But we could also go down here and look, what was the other course doing at the same time. So that's the track option. And I also want to show you this command, trace.stat symbol. This window shows you how much time the CPU spends in different functions. So we also have this info for all the cores, it's core 0. And if we go down, we also have the different cores. So let's go back to the PowerPoint presentation. That was it for the SMP system. And for the AMP, this stands for asymmetric multiprocessing. And you would use this if you have cores of different types. And you can see one example in the picture. That is actually the AMP system that I'm going to show you. So we have one SMP system, the one that we just took a look at, with 4 A53 cores, and we will have an R5 cores. And this will be considered as one AMP system. So we will have one trace 32 instance, the one that we already have open, and I will open up a new one for the R5. And yeah, the SMP system, the same rule applies. You still have to have the same cores inside the SMP system. And for the single cores, they can be bare metal, they can run OS. That doesn't matter. So this is the script that I will run in a very short while. Oops. So I have already ran this script, so we don't have to do that. Let's jump over it. And this is the command to open up, or this is actually the command to rename this window right now. So it will get renamed to A53, and then we will simply open up a new instance and name it R5, and we will also have to select which core it is. I mean, which architecture. And then we are running some script to set up the new trace32 instance. And yeah, I'll explain these commands after I've run the script. So let's do that. So now I open up this new window. Let's see. So we have the trace instance for the A53 cores, and we have another trace instance for the R5 core. Let me just resize them. And let me bring up the sync menu. So what these lines did is basically just configure these settings for us automatically. So you could have done this via the GUI, or you could have done it via the commands. And what these options does is it controls when you start the execution and when you break. So in this case, when I start, then both of the instances will start, and when I break, both of them will break. But let's say I'm removing this slave go. This means that when I start this instance, because this instance is considered as the master right now, and this one is considered as the slave, then this one will not start running. So that is how you synchronize the execution between different trace32 instances. So let's say you want to put a breakpoint for one specific core, then you would do the same thing as I did before. We can put a breakpoint at sieve. You would have to put it in the trace32 instance, which is controlling the core, so to say. Let's put the breakpoint here, and let's say we want it to break only when it is core 3. We would do the same thing again. And together with the sync menu, then you can control which instances you want to stop and which instances you want to continue running, for example. So we have stopped at the breakpoint, and here you can see it also says stopped by external debug request. Okay, let's remove this. And you can select which cores you want to trace. So right now we have trace enabled for both instances. So if we bring up trace.list, we have the trace data for this instance, and we also have the trace data for the R5 core. And if you, because this trace buffer is actually shared between the different instances. So if you want to filter the R5 core, like let's say you don't want to trace the R5 core, you only want to trace the A53 cores, then you can simply disable it. And if we make a new recording, you will see that we don't really have any data in this instance. And you can also decide, like you only want to turn off the ETM, then you would simply go into the ETM settings and turn it off here. And then it would look a little bit different. Let's start a new recording and bring up this. So you can filter what trace data that you want to trace. And the last thing that I want to show you is, let's see. It's this command. So I already ran this script, so we don't need to run it again. But this script is used when you want to track windows across different instances. So let's try to bring up chart. Okay, we should turn it on and make a new trace recording. And when I press init here, I simply remove the trace buffer. And you will, okay, this one already has the track options, but if it didn't, you would have to add the track options yourself. Let's just wait a little bit for this to finish loading. And now when I click here, we simply get this line so we can see what these other cores were doing. And if you want to see code coverage, then you can simply go press here and press add trace buffer. Let's wait for it to load. And once you have added the trace buffer, then you can see, for example, the functions. And you can see the coverage here, which code has actually been executed and how much. You can see also the branches. But this trace data only shows for the R5 core. So you would have to do the same thing in this instance if you want to see the code coverage for this A53 cores. So let's go back to the PowerPoint. So this was everything that I wanted to show today. So let's see if there are any questions. Okay, I will give you guys a couple of minutes if you want to write some questions. Otherwise, I hope you have learned a thing or two and wish you a happy day. Thank you for joining. Oh, we have a question here. Could you maybe show us how to trace some peripherals like DMA? Okay, some people have already left, but I'll see what I can do. Trace peripherals like DMA. I'm not sure if I have done that before, so yeah, I think for the first question I will have to get back to you. If you could mail in that question to our mail, that would be good. And the second question, what was the difference between the two trace debuggers? I'm not sure I understand what you mean. Let's go back to the PowerPoint maybe. we're actually not using two trace debuggers. We're just using one trace, and this is the trace hardware. Oh, maybe you were asking about the on-chip and off-chip trace. Okay. Yeah, thank you. Yeah, please mail your question to this email, or I can just copy paste it too. Yeah, no need to email it.